Hi students, in this video I am going to talk about the interaction of molecules with light. Till now you have studied about two types of properties of molecules, physical properties and chemical properties. We are going to talk about optical properties of molecule. That is, how does a molecule interact with light? What happens when light shines upon a molecule? Now, before we can look at what light does to a molecule, we have to understand what is light. Now, this we have studied since we were in school, that light is a form of energy. What type of energy does light contain? So, light is an electromagnetic wave which is made up of two different energy fields. One is the magnetic field and the other is the electric field. And these two fields are perpendicular to each other. What do I mean by that is that electric field, when you hear the word field, is planar. Similarly, magnetic field is also planar. Now, these two planes are perpendicular to each other. That is the first feature of an electromagnetic wave. The second feature is that these fields are oscillating. Now, what do I mean by oscillating fields? Oscillating field means the polarity of the field keeps changing over time and over distance. Polarity of the field implies the anode and the cathode of the electric field and the north pole and the south pole of the magnetic field. They will keep flipping over time and distance. So as the electromagnetic wave is moving, the north pole and the south pole will keep flipping and the anode and the cathode will also keep flipping. And this gives rise to a wave-like form of this electromagnetic radiation. Now, because it is a wave, it contains all the features of a wave. It will have an amplitude. That means this wave will have a certain height or a depth. So the height of the peak is called the amplitude, and it will have a wavelength. The wavelength is defined as the distance between two consecutive peaks or the distance between two consecutive troughs, and that defines the wavelength. Now, where does energy go here? So the energy of the electromagnetic radiation is quantum in nature. Every time students hear the word quantum, they get a little wary and say physics centers. But what do I exactly mean by light being a quantum phenomenon? Light can be quantified. Now, why do we say this? We say this because when light or units of light hit a certain metallic plate, they lead to the emission of electrons. Now, the number of electrons that are released is directly proportional to the amount of light that is hitting the metallic plate. So if less light hits the metallic plate, you get less electrons. If more light hits the metallic plate, you get more electrons. This experiment showed scientists that light can be quantified. So I can find a minimum unit of light that will lead to the eviction of a single electron. And that is what is called a quantum of light or a photon. Now, what does this correspond to? It corresponds to a single wave of light or a single wavelength. So this tells you that the energy of a photon is related to the wavelength of light. So the visible light, so electromagnetic spectrum is a huge range of electromagnetic waves that can be as long as a meter in case of certain radio waves and as small as a few nanometers in the case of gamma rays. The light that we see as sunlight is a small range which is called as the visible spectrum, which scans from 400 nanometers in the violet to 700 to 800 nanometers in the red. If the wavelength is less than 400 nanometers, it is called ultraviolet. If the wavelength is more than 800 nanometers, it is called infrared, and so on and so forth. Now, as I just said, a single wave is a photon. So wavelength corresponds to energy. And this relation is given by the Planck's relation, which states that E is equal to h nu, or E is equal to hc upon lambda. E is the energy, h is the Planck's constant, nu is the frequency of light. This frequency can be calculated knowing the speed of light c and dividing it by the wavelength. So this tells you something very important, that E is inversely proportional to wavelength. The longer the wavelength, the lesser the amount of energy. Now, if we have understood the relation between the wavelength of light and its energy, now let us bring in matter or molecules. What will happen to molecules when I hit them with photons or these small packets of energy of light? Depending on the energy that is hitting the molecule, if the wavelength is less, that means the energy is high, this energy is capable of hitting an electron. The wavelength is so small that it is capable of hitting an electron in the atoms of the material, and it has enough energy to cause the electron to leave the attraction of the nucleus or the protons and escape the atom. This will lead to deficit of an electron or generation of a positive charge, or what we call as ionization. When we go to slightly higher wavelengths, so here we come to visible light. Visible light has longer wavelength and therefore it has lesser energy. When this light hits an electron, it does not have enough energy to cause ionization. However, I am providing enough energy for the electron to move a little farther away from the nucleus and or go to a higher energy level. If I go to longer wavelengths, now I've reached microns in the infrared range, the wavelength is so large that it cannot hit an electron, but it can interact with molecules. And what it does when it interacts with molecules is it causes molecular vibrations. We will look into this more when we talk about IR spectroscopy. Now, when we are talking about visible light's interaction with matter, as I said, visible light causes excitation, or it makes the electron move to a higher energy level. I'll take 2 minutes to explain what this means. The electron that is present in the atom is held in its position because it is pulled by the nucleus, which is the hub of the positive charges. So for the electron to maintain a certain distance from the nucleus, it needs energy, right? Otherwise, the electron would fall into the nucleus. Positive, negative attract. But the electron is held at a certain distance. So if I have to keep them apart, I have to invest energy. And that is the energy of the electron, the potential energy of the electron. And that is why the positions of the electrons around the nucleus are called energy levels. So when this electron gets hit by a photon, it will absorb the energy of the photon, and the molecule goes to an excited state. What do I mean by that? Is that the electrons have now absorbed energy, so they can now move farther away from the nucleus or to a higher energy level. Now, a little revision about energy levels when it comes to electrons in a molecule. When we're talking about biomolecules, most biomolecules have covalent bonds, which means there is sharing of electrons between two nuclei. Now, these electrons form shared orbitals. So p and s orbitals get converted into sigma and pi. Now, when you have electrons in the sigma orbital, this orbital is present right in between the two nuclei. So it is being pulled by two nuclei. To keep it in its position requires a to make it jump to a higher energy level will require a lot of energy, because it's not held by one nucleus, it is held by two nuclei. However, when we come to the electrons shared in pi orbitals, this will be the region of the pi orbital where the electrons are placed, those electrons that are shared between the two, right? Now, these electrons are slightly farther away from the nucleus, so they have higher energy. Now, where these electrons have to move is the free space here, or the area away from this central zone where the effect of two nuclei is present. These are called the anti-bonding orbitals, the orbitals which are not shared in the between the two nuclei or are not a part of the bond. So I have bonded electrons. These are those electrons that are being shared between the two nuclei. And I have non-bonded electrons. These are those electrons that are not shared between the two nuclei. So the bonded electrons are technically held by two nuclei. So their potential energy is very, very low, and it requires a lot of energy to make them move from their place because they are being held by two nuclei. Whereas non-bonded electrons are held by a single nucleus and they are slightly farther away from the nucleus. That is why they're not involved in bond formation. And so their inherent energy is high. So making them jump to a higher energy level becomes easier. So what do I mean by this? Is that those electrons that are in the sigma orbital have the lowest amount of energy. Then you have electrons in the pi bonded orbitals because they are slightly farther away from the nuclei. And the highest amount of potential, inherent potential energy is present in the non-bonded electrons. Now, when I present or project visible light onto these electrons, visible light is between 400 and 700 nanometers. This energy is enough to cause non-bonded or free electrons to go to the pi star or anti-bonding orbital. Now, if you can see, this is the N, or the non-bonded electrons are present here. They are not shared. These can migrate to the anti-bonding orbital, that is the other side of the pi orbitals which are not occupied by the bonded electrons. When we go to slightly higher energy, for example, UV light, that is between 200 to 400 nanometers, lesser wavelength, longer energy, this energy is enough to cause electrons from the shared orbitals, that is the pi orbitals, to go to their anti-bonding side. Okay, so pi to pi star transitions are possible in UV light. Now, what do I mean by this? When the light is capable of making an electron jump to a higher energy level, that light will get absorbed by the electron and the electron will jump to the higher energy level. Okay? This means that when I have the entire visible spectrum or the sunlight shining on an object, that object, the electrons in that object, will be capable of absorbing certain wavelengths of light. These wavelengths will get absorbed and the electron will jump to a higher energy level. Whereas those wavelengths that cannot get absorbed will get reflected. So absorbance is what is responsible for the color in our world. For example, why is the leaf green in color? Leaf contains a molecule that is capable of absorbing light, that is chlorophyll. So this chlorophyll that is present in the leaf is capable of absorbing the entire white light spectrum, that is Vibgyor, except green. So it does not absorb green light. It absorbs violet, indigo, blue, yellow, orange, red, does not absorb green. So green gets reflected and that is what we see. And that is why the leaf is green in color. This is reflected in what we call as the absorption spectrum. So the absorption spectrum is the plot of absorption probability against wavelength. So if we take chlorophyll and we look at what are the lights or the wavelengths that it is absorbing, you will see that it absorbs in the blue region, it absorbs in the red region. The region where it does not absorb anything is the green region. And that is why chlorophyll and the plant is green in color. So we come to the end of this video. It tells you that the light gets absorbed by certain molecules, and this absorption leads to the jumping of the electron to a higher energy level, and only those lights that can cause these jumps are absorbed. And if a light is absorbed, that light disappears when it hits that object. The other lights can either pass through or get reflected, and that is how we observe colors. If you have any questions related to this content, please post them in the questions in the comment section. Like the video if you understood what I was trying to explain, and subscribe to my channel for more interesting explanations on biophysics and biochemistry. See you.